In Unit 2, entitled Center of Attention, it says, "Finally, we shall place the Sun himself at the center of the universe," which is Nicholas Copernicus. He was the one who established the heliocentric model for the atom, which is what our idea of the atom is based on, is the heliocentric model of the universe, where the Sun is at the center. So, the learning goals: students should be able to identify the atomic number and atomic mass based on the composition of a nucleus, and you should be able to identify the subatomic particles in the nucleus based on what is called nuclear symbol notation. Now, what we already know that protons and neutrons are in the nucleus, and so that's the center part of the atom. Okay, and we also know the nucleus is the center of the atom. And in the present, or in the lab, we learned that changing the number of protons, also known as the atomic number, okay, which is the number of protons, changes the identity of an element. So if something has one proton, it has to be hydrogen no matter what. If it has two protons, it has to be helium no matter what. Changing the number of neutrons does not change the identity of the element, but it does change what is called the atomic mass. The nucleus is the center of the atom. It contains all of the positive charge. So you see these things right here, the red ones are going to be the positive charge. These blue ones here are neutral, which means they have zero charge. And it contains 99.9% of the mass of an atom. The only thing that it does not include is the electrons, which are very, very, very small in terms of mass. The nucleus is what we think of generally when we think of an atom. Okay, it's the positive, it's the mass, it's got everything, the center of the atom. It is what we generally think of when we think of atoms. The proton is often symbolized by a P with a plus that's a superscript. So it's not P plus, it's a P with a superscript plus. Kind of like a squared symbol, but a plus, not a number. Okay, a proton is considered to have a charge of +1. So if you have two protons, this would have a charge of +2. Okay. A proton is generally considered to have a large mass. Now, this is a relative term. Okay, it has a large mass for something that its size is. It also is extremely dense because not only does it have a large mass, it has a very small volume. So it determines the identity of an element. So since this thing has two protons, it must be helium no matter what else. Neutrons and electrons do not matter whenever you're looking at the identity of the element. All that matters is the number of protons. And the number of protons is often referred to as the atomic number. Next, you have the elements and the protons. The number of protons determines the element. All carbon atoms have 6 protons. All hydrogen atoms have 1 proton. So the number of protons is equal to the atomic number. Okay, I can't emphasize that enough. So every time you see this number right here, that right there is telling you the number of protons. This right here is telling you the number of protons. Okay, that's telling you the number of protons, not anything else. It does help as far as aligning things up on the periodic table, but it's really important that you know that that top number refers to the number of protons. Next, you have neutrons. Neutrons are often referred to as an N with a 0. That indicates that it has 0 charge or that it is neutral. Okay, it is called the neutron because neutral, neutron. Okay, neutral charge particles. So you see these right here. These are the ones that have no charge. Likewise, they have a large mass. They have pretty close to the same mass as a proton. Okay, the mass of a neutron and the mass of an electron are pretty close. The neutron is actually slightly heavier or slightly more massive, but they're very, very close. They do, once again, occupy a very small volume in the nucleus. The nucleus is a very small volume compared to the rest of the neutron has an effect on different elements by the way of atomic mass. The atomic mass represents the number of protons plus the number of neutrons and is represented by this bottom number right here. This 12.0107 represents the atomic mass. Now, generally speaking, we round that to kind of a whole number, so we would call carbon, and we would say it has an atomic mass of 12. So what that means is it has 12 is the number of protons plus the number of neutrons. Now, since I know that this atomic number right here represents the number of protons, I can say that for carbon, it has 6 plus the number of neutrons. What that tells me is that carbon has 6 neutrons. When we do it for hydrogen, hydrogen has an atomic mass of 1. It has 1 proton, so therefore it must have 0 neutrons. Next we have isotopes, and isotopes are atoms with the same number of protons because that's what makes something the same, but it has a different number of neutrons. So what you see here is traditional hydrogen. Hydrogen has a single proton and no neutrons. Then you have what's called deuterium. Deuterium is a special isotope of hydrogen where it has one proton and one neutron. It has two things in the nucleus, hence deuterium. Tritium is where it has three things in the nucleus. 1, 2, and 3. Now, the isotopes of hydrogen are really the only ones that have special names to them. The rest of them are just referred to by the number of each subatomic particle that they have. So, all isotopes are the same element. So, hydrogen, deuterium, and tritium all react the same way. In fact, you probably have some deuterium and some tritium in your body just because there's a certain percentage of hydrogen atoms that are deuterium and tritium. Now, we can express isotopes in what is called nuclear symbol notation, and that's what you see right here. Nuclear symbol notation, you identify the number of protons that it has, and that is used to determine the element. This right here is the number of protons. The number of protons will tell you that since there's two, this has to be helium. So you write the chemical symbol for helium. You write the atomic number on the bottom left corner in the front, and then what you do is you write the mass number on the top left corner. So this right here is the mass number for helium. So if I were to look at the top helium, this top one, it says it has two protons and it has two neutrons. When I look at this version of helium, it still has those same two protons, but instead of having two neutrons, 2 and 1, it only has one neutron. So you have to get some practice as far as reading and going back and forth between nuclear symbol notation and the number of subatomic particles, but this is what you have as far as going back and forth between them. The atomic number, the atomic mass, and sometimes in the next presentation we'll talk about the idea of protons and electrons. Okay, so what is the major difference between a proton and a neutron? Their mass is the same. Okay, so that's not it. Their location is the same, so that's not it. So it turns out that it's the charge. The charge is the difference. A proton has a charge of +1, a neutron has a charge of 0. Determine the number of protons and neutrons in the element below. We look right here. Remember, that's the atomic number. So when I look at that, I can say 36 protons is what it is. Now remember, this represents the number of protons plus the number of neutrons. So if I subtract the number of protons, that will tell me the number of neutrons, and if I do that, that would be 42. So you have 42 neutrons. Okay, 36 plus 42 add up to 78, which is the atomic mass. When it says to write the correct nuclear symbol notation for the element below, the first thing we do is we have to take the protons and we look at the periodic table and say which one of these elements has an atomic number of 8, and that is oxygen. So with oxygen, I write the O, and then I write the number 8 right there because those two always go together. Now this top number has to be the number of protons plus the number of neutrons, so that would be 18. A mastery level question says carbon has an atomic mass of 12.0107. So can an atom have 0.0107 of a neutron or a proton, and to justify your answer? And the answer is of course not. If you have a proton and you cut it into pieces, you can't take that piece and say that's the piece of a proton that carbon adds to it. It either has 6 neutrons or 6 protons, or it doesn't. It can't have a partial proton or a partial neutron. Where that comes from is the idea that carbon has different isotopes. So there's one carbon isotope that's carbon 12. That's the most common. There's also a carbon 13, and there's even a carbon 14. Whenever you take these and you average them together, it comes out to be 12.0107. Now some of you may be saying, well, when you average 12 and 13 and 14, you get 13. And that's true. But it's closer to 12 because there's way more carbon 12 than any of these other two isotopes. And that's what we get when we call average atomic mass. The average atomic mass just doesn't depend on the fact that there's a 1, a 2, and a 3. It depends on how many of them there are. For example, 99.98% of all hydrogen atoms are regular hydrogen. Only 0.0115% are deuterium, and 0.0005% is tritium. So when you look at the average mass, you have to take into account what percentage there is of each isotope. So when you find the average atomic mass of hydrogen, it's like 1.00794, which means it's way, way closer to what this is than what it is to deuterium or tritium.